All right, let's work another example. So this time I want the antiderivatives of x cubed over root x squared minus 1. And I say where the domain of my function is x values bigger than 1. All right, so this time I told you the domain. So if you look at this square root here, you could plug in values less than -1 or bigger than 1 into the square root and it would make sense. But I've restricted the domain. So we've got an annoying square root in this problem. Well, trig substitution is going to allow us to get rid of that annoying square root. So we look at x squared minus 1. And we say, oh, it looks like secant squared minus 1. So you got to say, well, wouldn't it be great if you had a secant theta in there instead of x? If you did, you would have square root of secant squared minus 1, which would be square root of tangent squared, which would be absolute value of tangent. You would get rid of the square root. So we got to say, okay, well, let's let x equal the secant of theta. But then we got to say, well, wait a minute. Can we do that? I mean, is this cheating? Like, is this possible? Does this work? Well, let's look at a graph of secant. So secant. Secant hits all numbers bigger than 1 for angles between 0 and pi over 2. So no matter what x is, choose x to be any number you want. Choose x to be 5. Secant of theta, so let's say x is 5, let's say that's up here. Secant of theta will eventually hit 5. If you choose the right angle theta and you plug it into this function, secant of theta will give you whatever number you pick. If you pick 5, you can find an angle, where if you plug it in, secant of theta hits 5. So if you choose the right angle, you can always find an angle theta that corresponds to your x value. So I can indeed say let x equal secant of theta if I pick theta correctly. Theta, well, I can always choose theta to be an angle between 0 and pi over 2. All right, now look what happens. Take derivatives, dx d theta is, all right, derivative of secant is secant tangent. Multiply both sides by d theta. I get dx is secant theta, tangent theta, d theta. And now I just replace stuff in my integral. So x, I'm replacing it with secant theta. So on top, I'm going to have secant cubed theta. On the bottom, I have square root of secant squared theta minus 1. And then I am replacing dx with secant tangent theta, or secant tangent d theta, like that. Then we say, okay, well, the square root of secant squared minus 1, we're going to make that disappear. Secant squared minus 1 is tangent squared theta. I have secant theta, tangent theta, d theta. Square root of tangent squared is absolute value of tangent. And now we're in the same scenario that we were in before, where we're like, oh man, I really want to cross off these tangents, but I can't because of that absolute value. So we got to say, well, can we do something about those absolute values? Well, it turns out we can. So if you look at a graph of tangent, you say, well, what's going on with tangent? We picked our angle, theta, to always be between 0 and pi over 2. Well, look at tangent. Between 0 and pi over 2, tangent is always positive. So if you pick an angle between 0 and pi over 2, tangent's always positive. Well, wait a minute. That means those absolute value bars then aren't doing anything. If tangent's positive anyway, then the absolute value of tangent's just plain old tangent. So again, I can just drop those absolute value bars. And I'm left with this. Now I can cross off the tangents. And I'm left with finding antiderivatives of secant to the fourth theta d theta. Secant times secant cubed, secant to the fourth. All right. So, trig integral. Okay, I'm going to make this look like stuff with tangent in it times secant squared. So I'm going to pull off a secant squared so that I have secant squared theta times secant squared theta d theta. And then I'm going to say, okay, secant squared. I can replace that with tangent squared plus 1. So I have tangent squared theta plus 1. I replace that first secant squared with tangent squared plus 1. And then I got this guy. Yay, now I have stuff with tangent in it times secant squared. So I can let u be the tangent of theta. So du d theta is secant squared of theta. So du is secant squared theta d theta. All right. So I replace tangent to theta with u. So I got u squared plus 1. Secant squared theta d theta. That becomes my du. All right. An antiderivative of u squared, u cubed over 3. An antiderivative of 1 would be u. Don't forget my plus c. All right, so again, we're not done. We got an answer with u's in it. Our problem started with x's. So then we say, okay, well, u is the tangent to theta. So now I got tangent cubed theta over 3 plus tangent to theta plus c. Now you got to say, okay, wait a minute, I still don't have x's in my problem. Now x was the secant to theta. I want to simplify tangent to theta. So let's draw a little triangle here. So x is the secant of theta. Think of this as x over 1. Then this is your hypotenuse divided by the adjacent side if you draw a triangle. So theta is chosen to be an angle between 0 and pi over 2. So it's an angle in this quadrant here. All right, so I draw a triangle. There's theta. Hypotenuse is x. Adjacent side is 1. Using the Pythagorean theorem, we'll get this side here. It will be root x squared minus 1. So now, what was the purpose of this? Well, the idea is we're using the triangle trick here. We can say, great, I can get the tangent of my angle now. The tangent of my angle is opposite over adjacent. Root x squared minus 1 over 1. In other words, it's root x squared minus 1. All right. So, back to our problem. Okay. Tangent. We're replacing tangent with root x squared minus 1. Well, it's supposed to be cubed, so we're going to cube that. Put it all over 3. Plus root x squared minus 1 plus c. And we're done.